So, good evening, everyone. We are going to start our sixth session on desalination and wastewater treatment by membrane technology. And we have Dr. Swatantra Singh as a moderator for this session. He is an assistant professor in environmental science and engineering department at IIT Bombay. His research area mainly includes membrane fabrication, environmental nanotechnology, fate and transport of pollutants and emerging contaminants in the environment. He has 4 US patents on membrane and laser-based graphene fabrication techniques and has published 19 journal articles in high-impact journals. So I would like to invite Dr. Swatantra Singh for carrying the session forward.
Thank you. So let me share the screen. So welcome everyone, and this is the theme 6 for our conference organized for this is the 5th chapter of this international conference on organized by the International Society of Energy, Environmental and Sustainability. And here we are going to talk about desalination and wastewater treatment by membrane technology. And we have 3 speakers, and I will also going to give a talk. So there will be 4 talk in this session. So we have Professor Chris Arnush and Professor Roni Kasher from Ben Gurion University of the Negev, Israel. And this institute is a pioneer in membrane technology because after doing his postdoctoral studies of Sidney Leo, which they were like with another Indian scientist, they have first to fabricate the RO membranes, and he joined the institute, and they started making the plants, and first community plants for RO membrane based plant was made by the Ben Gurion University. And third, we have Professor Tabish Nawaz. So he is assistant professor in environmental science and engineering department of IIT Bombay, and he's working on different aspects. And one of the things where he's working is the try to recover the resource recovery from the RO concentrate. And myself, I'm working in a different aspect of membrane technology, and so I'm going to talk about the biofouling. So just briefly, so we will start with Professor Kasher, and he's going to talk about silica scaling during brackish water, reverse osmosis desalination studies by membrane surface mimetics. Then Professor Kiss will talk on laser-induced graphene membranes for contaminant removal and other developments what made. Then Professor Tabish on resource recovery opportunities from reverse osmosis concentrate, and then I will talk on biofouling. So with this, I would like to invite Professor Roni Kasher, so he can share the screen, and meanwhile, I will give his introduction, the brief introduction about him. So I request Professor Kasher to share the screen, and I request attendees to put their question answer in Q&A section, and all the questions we will address after all 4 talks. So Professor Kasher, please. Yeah. So just I will introduce Professor Kasher. So Professor Kasher has done his BSc and MSc from the Hebrew University of Jerusalem, Israel. And basically in his MSc in organic chemistry, he has worked on development of photocatalytic system for electrical communication between enzyme and synthetic polymer. Further, he finished his PhD from the Hebrew University itself in organic chemistry, where he has worked on design and synthesis of backbone cyclic peptide and mimic proteins. After that, he has done his postdoc from Weizmann Institute of Technology, where he worked on rational design and synthesis of biological active peptide, design synthesis of peptide and estrogenic activity. At present, Professor Kasher is a professor at Zuckerberg Institute of Water Research, which is part of Ben Gurion University of Israel. So this Ben Gurion University has 3 campuses, one in Beersheba city, another where this Zuckerberg Institute of Water Research is there. So it's a small place. It's called Sadeboker, and third is in Elad. So Professor Kasher is working on mainly on the noble membrane for water desalination and treatment. So he's trying to develop new methods, he's developing new approaches to do the surface modification to deal with different kind of fouling, mainly the scaling. And also there are many other things where he tried to come up with new generation of nanofiltration membranes. And today Professor Kasher is going to talk about on his work on silica scaling during brackish water reverse osmosis desalination by using some mimetic surfaces. So I would like to invite Professor Kasher. Please, you can start. Thank you.
So thank you very much, Professor Singh, and I thank the organizers for inviting me to speak in this conference, very important conference with the interesting topics. So I would like to start by describing the importance of desalination of brackish groundwater, especially in dry and semi-dry areas. So here you can see the map of Israel with the precipitation, annual rainfall, the average annual rainfall. And you can see, just a second, let me have the pointer. Okay, so this is the arid and semi-arid areas just by the annual precipitation. And you can see that more than half of the country is a desert. You can see it is about 60% of the country. By the way, this is Sadeboker campus. This is our university campus. As Professor Singh mentioned, this is a campus. It is located in the middle of the desert, and we are specialized in desert studies among our current research. The main campus is located here. So if we are looking now on the brackish groundwater desalination facilities in the state of Israel, you can see that most of these facilities, almost all of these facilities are located in the desert, in the arid or semi-arid regions. And this is by itself tells us that the importance of these water resources, because in these regions, this is the most reliable water resources. Now, if we look on the global distribution of climate zones, we can see the large fraction of the arid and semi-arid regions globally. So by that, we can understand the importance of brackish water, the groundwater desalination globally. Now, what is the brackish water? It is defined as the water, natural water with 1,000 to 10,000 milligram per liter. In most cases, it is between 1,000 and 3,000 milligram per liter. So the advantages of brackish water desalination is that it has much lower salinity than seawater, which is lower energy demand. It is available inland. And the challenges of brackish water desalination is the brine disposal. The other characteristic that it has diverse water chemistry, which is located. It depends very much on the location and the type of aquifer. There is usually high sulfates, which cause gypsum scaling, and silica scaling, which limits the recovery. In this talk, I will focus on silica scaling. So the silica scaling in brackish groundwater, here you can see the solubility equation of silica. It has 120 ppm solubility. The problem is that acid wash is not effective. Alkaline pH dissolves silica, but might cause a carbonate precipitation, and there are no efficient anti-scalants. So the objectives of this study was to study the influence of surface chemistry on silica precipitation in conditions that simulate desalination of brackish groundwater. So we construct a solution that simulates desalination of brackish groundwater, fabricated surfaces with unique chemistry, and determine the effect of surface chemistry on silica precipitation. Now, it is very important to keep in mind that with silica, we have two modes of precipitation. Because of this equilibrium between monomeric silica and multimeric silica in solution, we can have a heterogeneous deposition, which means the deposition of monomeric silica on the surface and further crystallization, mineralization. Or we can have the precipitation in solution, then precipitation on the or adhesion to the surface, and followed by further mineralization. So in the first step, we prepared the model solution that simulates brackish water desalination. We based our solution on the RO concentrate of the Negev Highlands groundwater. There is, as you saw before, there are several desalination facilities for brackish groundwater, and here you can see the composition of this groundwater. The main differences, and here on the right is the model solution. So the main differences were that silica concentration was increased to be more than higher than the solubility, and sulfate was reduced to avoid the gypsum precipitation. We also added a buffer. This is an organic buffer that keeps the pH at 6.5. So the solution was stable for at least 24 hours. Here you can see this is the monitoring of the solution in time by measuring the turbidity and the silica concentration in solution. So for at least 24 hours, it was stable. Next, we prepared the surfaces that with unique chemistry by using self-assembled monolayers of alkylthiols on gold. So this is the alkylthiol with different functional group X. We use this list of different functional groups. You can see the quaternary ammonium group, carboxylic acid, OH group, and etc. Then we measure the water drop contact angle, and you can see that they have diverse wettabilities. So these the same principle of modification or synthesis was used to coat quartz crystal microbalance sensors by the same monolayers, and this will allow the monitoring of silica precipitation. So here you can see the results of quartz crystal microbalance monitoring of silica precipitation in time. Now, the first line is the model solution without silica. You can see that there is no precipitation. I forgot to say that here in the QCM measurements, the larger delta F is the larger precipitation. So we can see also that the neutral surfaces, like this hydrophobic alkyl surface, did not have intense precipitation. On the other hand, surfaces with positively charged groups like quaternary ammonium and ammonium group had very intense precipitation during the 24 hours. The negatively charged group are the carboxylic acid and the phosphate group had very minor precipitation. You can see here, this is the summary of the precipitation after 18 hours in all of the different experiments. So we can see again that the positively charged group had very intense precipitation. Next, we use the AFM to measure the interaction forces between silica colloid and the different surfaces with alkylthiol groups, as you can see here. So the interaction forces can tell us, can indicate the adherence or the attraction, and therefore we can learn about the potential precipitation. Here, the bottom two graphs, you can see two examples of force versus distance measurements. On the left is the carboxylic acid group. We can see that there is hardly any force was measured. And with the ammonium group, which is positively charged, we can see a very large peak, which implies for a high interaction energy. Here you can see other examples. This is the gold, the bare gold, the alkyl group. Here, this is a mixture of carboxylic acid and amino group, and here is the ammonium, quaternary ammonium group. So we can see here the same trend as we saw by the quartz crystal microbalance measurements, that positively charged group here in the AFM were shown to have a very large interaction energies. And unlike the neutral groups, here, for example, that had almost no interaction energies. So this is the summary of the interaction energies between the silica colloid and the surfaces against the calculated surface potential here in the x-axis. So we can see here, this is the interaction energy. And the more negative interaction energy, the higher intensity of interactions. So we can see here that the quaternary ammonium group and amino group had the highest interaction energies, and the negatively charged groups, like the carboxylic acid, had a very, even a positive energy, which means that very low interaction, even repulsion. So, and this is the gold and the alkyl groups. So this trend is in agreement with the findings from the QCM studies that measured the precipitation of silica from solution. So the conclusions that surface functional groups significantly enhance or influence, silica precipitation in brackish water desalination. The positively charged groups, amine and quaternary ammonium, induced more intense silica precipitation, and precipitation increased due to electrostatic interactions between the positively charged surfaces and the negatively charged silica. Now, if we look on these schematics, we can see that on the left-hand side, the heterogeneous deposition, we have the monomeric silica, which is neutral. Then it binds to the surface, and we have the precipitation process here. Now, solid or silica particles are negatively charged. So if we have a positively charged surface, this will stabilize or have more stabilization of this precipitate silica. On the other hand, the homogeneous precipitation, we have silica colloids in the solution. They are attracted to the positively charged surfaces, which increases the local concentration and induce mineralization. So I want to acknowledge the people who took part in this work. Kartik Ratinam, Dr. Kartik Ratinam, he did a postdoc. Here you can see in the picture, he did most of this work. Dr. Shijo Abraham and did a postdoc. He did all the AFM studies. Professor Yoram Oren, Dr. Yair Kaufman, and our collaborators from Germany, Dietmar Schwan and Winfried Petri from Technical University of Munich, the German-Israel Foundation for Scientific Research for financial support, and I thank you for your listening.
Thank you, Professor Kasher. So please, I request attendees to put their questions in a Q&A section, and we will take all the questions after all 4 talks. So now I would like to invite Professor Arnush. He can share the slides, and I will give his brief introduction. So Professor Christopher Arnush has done his BSc from University of Alberta, Canada, from Department of Chemistry, and then he has done his PhD from University of Utrecht from Netherlands, and from the Department of Medicinal Chemistry in 2005. And after that, he moved to Israel for his postdoctoral studies at Weizmann, and he worked there on peptides. And then he joined as a assistant professor at Ben Gurion University of the Negev, Israel, where he's working on different kind of new technology to fabricate RO and ultrafiltration membranes, and also the new kind of graphene-based surfaces, such as the laser-induced graphene. And his lab is the one of the first people to start using laser-induced graphene for desalination and wastewater treatment purposes. So with this, today Professor Arnush is going to talk on laser-induced graphene membranes as electrically active filters for contaminant removal. So welcome, Professor Arnush. Please go ahead.
Okay, thank you. Thank you, Professor Singh, for the introduction. And yeah, a lot of my work I've done together with Professor Singh. He's a current collaborator, and also he spent time here at our institute in the past. So today I'll explain to you, first of all, Professor Kasher, we're also close colleagues. So he explained where we are in Israel, and you can see that we're in the middle of the desert. So, however, our institute is a very beautiful place. It's situated in the desert. We've got a beautiful campus. There's about 300 students here, so it's very small, but the labs are all brand new. And here are some pictures of the campus. So here is also a picture behind my house, and how can we get water into the desert? Well, Israel now has got a very good water distribution system. So we are very comfortable here in the desert, but that was not always so. And that was mainly due to desalination technologies that Israel pioneered. So I'll be talking to you today about a new material that I've been using for the last about 4 or 5 years on surfaces, and it's a material called laser-induced graphene. Basically, taking a common laser, a CO2 laser that you mainly use for cutting, if you tune it down, you can treat different polymer surfaces with this laser, and you can convert the top part of the polymer surface into this laser-induced graphene. So this is just a picture. This is what it looks like on the SEM, so you can make different patterns. This is a zoomed in pattern, so it's a porous material, porous carbon material, And you can see down here with the Raman and the XRD that it's got the typical DG and 2D peaks of graphene. And so here we started, or it was shown first in 2014 by another one of my collaborators, Professor Tour at Rice University. He discovered this new method on polyimide. And so here is a picture of the cross section. And you can see that a portion of that polyimide was converted to laser-induced graphene. So it's a conformal way to make conformal coating. So a coating which covers the entire surface. And because it's porous, you can see it's full of pores. And in our department, we're working with porous membranes. It is a very, very interesting material to work with. So this is basically what the process looks like. You put a substrate into the laser, and as the laser goes back and forth on the membrane, you see a tiny flame happening here because you heat the surface up instantly to 1,000 degrees Celsius or more, instantly converting the polymer, which can be just a polyether sulfone seen here, into a carbon. And also because of the wavelength of the laser, the carbon-carbon bonds also absorb that energy. So this, due to this photothermal effect, you get a graphene material on the surface. So this graphene, if you know, it's also electrically conductive. So here's just a simple way of putting a battery in between two strips of laser-induced graphene, and you can see it conducts electricity. So it's got a lot of interesting properties. You can control the surface hydrophobicity, hydrophilicity, the surface chemistry. It's electrically conductive. So we really think that this material has got a lot of possibilities for interesting surface effects. And so actually, I'll also be showing some work that Professor Singh and I have done together. This is laser-induced graphene. We put it on a polyimide sheet, and we discovered that it is both anti-fouling. You can see here that these bacteria, they don't really like to grow biofilm on the laser-induced graphene. But because of this electrical effect, you can put a voltage across the laser-induced graphene, and then you can actually get a bacteria killing effect. So we noticed that, okay, it's bacteria anti-fouling, and you can actively kill bacteria with it. So this is just a slide which shows that anti-fouling effect. So this polyimide and graphite as controls, you can see there's a lot of fouling here. So this green is just the stain that you can use in microscopy, which shows a live bacteria. Red means dead, and this blue means EPS. So it's kind of a component of biofilm. And you can see, so this LIG has really low amount of bacteria on the surface. And even on the same sample, on the LIG part, there's low amount of bacteria, whereas on the control right next to it, you get a large biofilm growth. And so I think Swatantra will speak of this later in the talk, but we also discovered that the properties of this laser-induced graphene, which is attributed to this anti-fouling effect, and we noticed that the structure is got a large role to play with this anti-fouling effect. So you can see here, it's not fouling with the structure, but when you crush the structure, you start to see fouling. So what we noticed also is that you can increase this effect by doping the laser-induced graphene with something, for example, like silver. So you put the silver salt into the precursor, and when you lase, the silver salt becomes silver nanoparticles. So you get silver nanoparticle embedded graphene, and here's the XPS and the Raman. You can see the silver in the graphene structure, and you can also see it with SEM, for example. You can see all these little white dots as the silver nanoparticles. And so you can see that the silver, since silver is known to have an antibiotic effect, you can see the silver in the LIG has both anti-fouling and antibiotic effects. See, this red is the dead bacteria. Without the silver, you don't see any dead bacteria, but you see just live bacteria. So you get this extra killing effect, and here are the pictures. The control is the green, that's the living bacteria. With LIG, you get the green, which is still living bacteria, but much less. And then jumping down here to the silver LIG, you get really no bacteria at all. And you can see, just analyze with the results here, only dead bacteria. So what else can you dope? You can also dope the graphene with different heteroatoms. So here's a sulfur doped LIG. So depending on the substrate, you can get different heteroatoms into the graphene structure. So here's a sulfur doped LIG. And we noticed that this sulfur doped LIG gave increased amounts of, for example, hydrogen peroxide when you use them as electrodes. And so when we put them in a configuration, this is a laser-induced graphene on a membrane. And when we stack these membranes in such a stack down here, you can put a voltage across it. And as you filter the solution, you can get inactivation of bacteria. So for example, this is just the bacteria removal. So you can see it. This is a membrane with very, very large pores. And you can get very huge fluxes with these membranes. And they don't really reject bacteria based on the pore size. These kind of membranes that we made in the house, they have much better rejection of bacteria. However, when you put the voltage across it, you can get you can get complete removal of the bacteria. So we use a 6 log of bacteria, and with 2.5 volts, we get 6 log bacteria removal. And this was at a low flow rate. When you do an ultra high flow rate, all we have to do is increase the voltage to get killing up to 6 log removal. So not only can we remove bacteria, but we can also remove a virus. So here's a vaccinia virus, a model virus through this LIG filter in the same configuration. So 0 volts, you can see the viruses are not affected. But at 5 volts, 10 volts, and 20 volts, the viruses are completely destroyed at these voltages. And even at 20 volts, you can see there's just nothing left of the viruses. So there's many different ways there's many different parameters to get different properties into the LIG. And one of the ways to modify the LIG is to laser the substrate multiple times. So there's different ways to do that. You can either defocus the laser, you could increase the image density so that the laser, every time it scans, you get multiple lasers. So this scan would laser this area again. Or you could just take the sample and laser it multiple times over and over. So here we took polyether sulfone membranes and we lased them multiple times. And what we saw is that the LIG, this top part, became a bit more dense and it became much stronger. This multiple lasing process, you can increase the amount of graphene content. So here's lasing 1, lasing 2, lasing 3, this surface where you laser it 3 times, you get a much better graphene. You can see by the D and the 2D peaks. And this better graphene gives a better hydrogen peroxide production. Okay, so it's better electrochemically. And so this multiple lased graphene is also more stable. So you can see here after sonication, the graphene, because it's kind of brittle, you sonicate it, it can be removed from the surface. You can see this first lasing. But the multiply lased graphene is more stable. So you don't get so much graphene removed. You can also see that as you lase more, the electrical conductivity goes up. So it's a way to increase the quality of the graphene. So what we did with this graphene is we tried to remove different model pollutants using this electrode setup. So what we do is just put the 2 electrodes in solution with an electrical current, and then you can get the electrochemical reactions coming. You can also put it in a configuration where you use this actually as a membrane. So you have feed, it goes across flow, you've got permeate. So both the membrane filters and you can get a degradation effect on the pollutants through this system. So we tested iohexol, carbamazepine, also methylene blue and chromium, so different model pollutants. So with methylene blue, just to kind of, just to see if it's working, and with electricity, you can see here's the normalized concentration estimated with just this decolorization. You can see down below here. So it is decolorized, but also when we checked the carbon content, we can see about a 40% complete mineralization at 2.5 volts. Carbamazepine, also you can see that compared to the control with no electricity with 2.5 volts, we can see degradation of carbamazepine. And we completely mineralized about 64%, and we could find only about 3.5% as degradation products. So we identified these degradation products using MS. So here, the iohexol removal, we could see that we can remove about 50%. Of course, since the LIG is carbon, it's kind of like activated carbon. It's also got the ability to absorb organics, for example. So you can see a little bit of absorption of the iohexol and about 50% degradation. And here we also identified degradation products using mass spec. Finally, chromium through the using the flow-through system, which is actually like a recirculated batch system, because we recirculate the feed until we get complete chromium removal. We've actually also done a flow-through system where we flow through just once through the system, and I'll just talk about that in a minute. But with this recirculated batch system, a flow-through system, so using the porous membrane system, we can remove almost a complete removal of chromium 6 using 3 volts of electricity. And you can see here that we can remove also some just with adsorption. So this chromium 6 removal, where does it go? It's actually converted to chromium 3, so it's reduced. And we can see it, the chromium 3, both in solution, we can measure it with ICP, but also we see the chromium 3 becomes precipitated and absorbing onto the membrane. So we can both remove chromium 6 to chromium 3, and then also absorb it onto the membrane. So here using XPS, the chromium 3 as chromium oxides are seen. So when we use the flow-through method with the same system, we see that the removal is much less. However, if you put membrane stacks, so stacking this membrane, multiple membranes, you can increase the removal of chromium, and the retention time is very important. So if there's ways to increase the retention time of the pollutant within the membrane, then you can get a higher removal. So conclusion, hopefully I showed you here, I focused on laser-induced graphene, but hopefully I've tried to convince you that it's a material with a high potential for water treatment and filtration, anti-fouling, electrochemistry. I didn't show you evaporation or distillation. I showed you a little bit of adsorption, and there's a lot more different things that we think can be done, even for example, pollutant sensing, which is summarized in this review paper here. So yeah, I'd like to thank you for your attention. My acknowledgements, this work was started as a collaboration with Professor James Tu at Rice University, Professor Jasby, people at Rice University, also my colleagues at Ben Gurion University has helped me a lot in this research. And of course, Professor Swatantra Singh, the moderator, it was a lot of his work I presented today. And then a lot of excellent postdocs from India have come to this lab and have participated in this laser-induced graphene research, and some students that are currently in my lab today. So thank you, Professor Singh, for the invitation, and I'll welcome questions in the session afterwards.
Thank you, Professor Arnush. So for this informative talk, so I request attendees to put their question in Q&A section, and we'll take after the all lectures. So with this, I will start my talk, which is so let me share the slides. So I'm going to talk about the biofouling control in the membrane technology and using the textured surfaces. So generally, like what happened, like, I will start with little more background because there are many attendees like they have very little information about the membrane technologies. So this is not new. It started long before, as in the beginning I told, like the first RO membrane was made in California, Berkeley, by Sidney Loeb and another Indian scientist. So it started in 1960s for desalination and water and wastewater treatment, but that time there was many challenges such as high energy requirement, and also there was not much materials for making good quality of membranes. What happened, especially after 1990s, there was a revolution in material science, and also along with that, there are many new setups came for energy recovery from the desalination units, and also with time, the water regulation became strict. So with this, membrane technology gained its use, and here in this, you can see it's giving a very wide option of treatment. You can do pre-treatment using microfiltration and ultrafiltration. And when you go more with reduction in a pore size, with nanofiltration and reverse osmosis, you can get a very high, good quality of water. And also there are debates like in reverse osmosis, generally there is no physical pores. So mostly the separation is happening on the basis of diffusion. And because of this, you have all you can use these membranes for different type of waters, for different type of waters. At present, the water use annual growth is 14% and desalination is 8%. And combinedly, it's giving thrust to the membrane technology, which have approximately 17% of growth rate, which is quite huge. So, but what happening if the price is still high, and it's seen the most of the things, the price is high because of the fouling. So what is membrane fouling? So any undesirable deposition of materials either on a surface of membrane or inside the membrane pores, it's fouling, and it's what it's done, it's reduced the overall performance and efficiency of the membranes, and it increased the cost, because if fouling is happened, you are not able to get the desirable quality, and also you have to put a lot of pressure, because when we are talking about these all these processes, ultrafiltration, nanofiltration, RO, all you have to put a lot of pressure, and then you have to invest in the energy, and it's automatically increasing the cost. Along with that, you have to put a lot of money for the cleaning of these membranes, and sometimes they are really irreversibly fouled, and in that case, you have to replace the membrane. So generally, the lifetime of your membrane module is less. And here in this picture, you can see we have 4 kinds of fouling, such as colloidal fouling, organic fouling, scaling, what Professor Kasher talked about, very important silica scaling, and the last is the organic fouling or biofouling. Last is the biofouling, and biofouling is the worst one, because here you can see here active live organism involved. So first they attach with the surfaces of the membranes, and then with the different stages, they finally grow and disperse and contaminate the different places in the membrane module. And according to the condition, the environment, this whole process can happen within few hours to few days. So this is showing the overall potential of the biofouling, and that's why there is a lot of work is also going for the biofouling. Other fouling also has created a lot of problem, and many researchers has working to control these fouling. But with the biofouling, here if you have enough nutrient and other things, so then this can go worse, and that can happen in a very short time. There are examples where it was reported like within few hours, the many big plants, when I visited, when I was a postdoc in Israel, we have visited one of the plant, and while talking about the plant, one of the engineers told us like a few years before, within few hours, the half section or like half plant of one of the desalination plant in Israel was stopped because of the biofouling. So it's very critical. People has to put a lot of monitoring and control, check these microbial contamination and what the kind of nutrients it's reaching to the main module, the RO module. If we are not controlling, it can create a lot of problems. So this is showing the potential of biofouling, and it can happen at very fast rate. And these are some of the digital and SEM images taken from the internet, fouled spiral wound membranes. So what is the possible solution? So generally at present, what people are trying to do, they have different kind of biocides. They are trying to clean the membrane, but also people use chlorine. But the problem, if you know, like these bacteria. So bacteria inside a biofilm, they are more resistant for killing. For example, here one of the studies have shows bacteria inside a biofilm, they are approximately 600 times more resistant for chlorine concentration. And also, if we are using a high concentration of chlorine, it can damage these RO and NF membranes. So the strategy, if you recall, like we were talking about the initial attachments, it's very crucial. So what scientists are trying to go, the research in going in a direction where they are trying to stop the initial attachment, or if the organism attach after that, then put something on the membrane that can inhibit the organism. So for that, different kind of strategies are the scientists are following. For example, they are doing surface modification. It can be a chemical modification where they are trying to change surface hydrophilicity, surface charge, surface roughness, and also making pattern to make a biomimetic surfaces. And in these strategies, what we are calling, if we are putting certain biocides on the surface of membrane, we are calling active strategies where we are putting biocides or different kind of nanoparticles to kill the organism. The other second strategy is the passive strategies where we can make a texture, and by that texturing we can reduce the initial attachment, and if we can reduce the initial attachment, we can delay the fouling for a long time, and in this process we can save a lot of energy. So what is in the nature, there are many examples for this kind of anti-fouling biomimetic surfaces, such as, like, if you can see, this is the SEM image of fly wings. So you can see there are many nanostructure on these fly wings. And similarly on shark skin, you can see it's a micro size texture is on that. And here in the smaller section, you can see there are even a smaller size of texture. And these surfaces have shown their potential for biofouling control. So and there are many research has been done on this area. People have tried to understand how a different kind of texture can force the organism to adopt a different kind of strategy for a biofouling. For example, in the first image, you can see there are different kind of pillars made, and the distance in the pillars was different, and on the basis of that, there was there is a change in deposition of these microorganisms has been seen, the bacteria. If the species are less, they can just grow in such a manner. And here you can see it's very difficult for these organisms to grow on that. And basically these pillars, the micro and nano size pillars, can destroy these bacteria. So by this, we can delay the attachment. Similarly, in another studies, people have shown how the different kind of fibers, if you put, then for organisms, it's quite difficult to sit on that because they are not getting enough area to sit and grow. So the overall interest, and similarly here in another studies where people have tried to mimic a sark skin with using this polydimethyl siloxane PDMS, and they make this kind of texture, and they have shown in 21 days a clear difference between these two surfaces. And on 14th date, they have estimated on the sarclate surfaces, there is less bacterial growth as compared to the plain PDMS surfaces. So basically, the overall where I developed these interests is come from the laser-induced graphene, because it was quite surprising for us. There are when we started working on this, when I was a postdoctoral student under Professor Arnush. So we have got extraordinary results from laser-induced graphene, and it taken us a month to digest that result, because when we have done confocal analysis, we have seen almost no biofouling on the LIG surfaces, and we were really surprised, like what kind of properties of laser-induced graphene is coming, giving such a result, because there are earlier results with graphene oxide, reduced graphene oxide, but in all those cases, no one have ever reported such kind of anti-fouling surfaces. If you can see here, we have done a control experiment with graphite, and we've seen a lot of biofouling on that. PI surfaces, a lot of biofouling, but laser-induced graphene, no fouling. So after we tried to understand how I tried to explain the overall things on the basis of hydrophilicity and surface charge, but we failed. Then what we realized, why not to play with the texture? So we made 4 kind of textures. So generally, one is your normal LIG surface, which has your micro-sized pores and nanofibers, and then we have crushed these surfaces. And then later also what we have done, we have used oxygen plasma to make these surfaces as super hydrophilic. So without crushing these surfaces, like we have retained the texture and that did the plasma, and we also crushed the surfaces and done the plasma. And when we done the experiment, the biofouling experiment with this set of experiment, you can see we have seen biofouling growth on crushed surfaces. And even on the crust plasma surfaces, we have seen more biofouling. So this shows, like, it's given us an idea, like the main thing why these surfaces are showing this anti-fouling properties is basically because of the texture. So also one interesting phenomena we have seen, like while changing, when we try to see the average size of the bacteria on different surfaces, like for example on polymer normal PE surfaces, we have seen the size was around 1.5 micrometer, whereas on crust we have seen crust LIG it was 0.9 micrometer, and on normal LIG on these crust LIG it was 1, and normal it was 0.9. So we have seen a reduction of this size. So what I have shown you earlier with some older the papers, the other papers, where these organisms, they change their strategy. If there is not enough surface area available, they are trying to change their shape, and that's why here from the rod shape they are converting into the circular shape. Or so this confirmed the overall thing why we are seeing this these anti-biofouling properties is because of these nanofibers and the micro-sized pores, and this combinedly both micro and nano, it's generating a kind of interaction and flow pattern where it's quite difficult for these organisms to sit on these kind of surfaces. So this has shown the potential how we can make a new kind of membranes, a textured membrane, and with the collaboration with Professor Arnush, we already have 2 ultrafiltration membrane. One is Geo LIG membrane, and another is PVA LIG membrane. But what we have seen when we are doing a surface modification, because remember Professor Arnush talked about that when we are burning these membranes, we are converting into the filters. So if you want to get ultrafiltration membrane, we have to go for we have to do another round of surface modification. And with surface modification, what we have seen, we have slightly compromised with the texture. So we have seen more biofouling formation as compared to the normal LIG, but it was comparatively lower than the the commercial membrane we got. Similar to that, and at present here in IIT Bombay, one of my students also trying to fabricate membranes, ultrafiltration membranes and NF membranes to modify with the polymer brushes. So the idea here is also the same, where we are trying to grow the brushes on top of the membrane, and these brushes, they are going to change along with the changing the surface property, they will also change the texture on the membrane, and that will help to reduce the biofouling. So in summary, biofouling is a major problem for the membrane technology. If we want to make a low-cost solution, especially in India, we're looking for low-cost things. So if we want to do it, we have to control the biofouling along with the other kind of fouling. So along with active methods, we can use these passive methods like texturing of the surfaces, and that combinedly with active and passive probably will deal with these kind of problem in a more effective way. Laser-induced graphene and polymer brushes have the potential to give us both low pressure and high pressure membranes. So we can have ultrafiltration and NF and RO membranes, and where we can make very compact system, anti-fouling compact system, which can give us the clean water. And we can use for different kind of sources. We can go for desalination or wastewater recycling. And also there is a huge potential with these both kind of membranes. We can play with the selectivity and permeability with both LIG and polymer brushes, because there is a lot of potential to do the surface modification and also make different kind of composite membranes. So the best strategy to delay the overall the attachment of the microorganism, and in this way we are going to delay the biofouling, and in this way we are going to save a lot of money in terms of energy as well as the increasing the life of the membrane. So for this, I would like to acknowledge my postdoctoral supervisors, Professor Arnush and also Professor Toor from Rice University. And also there are, because of the corona, things got delayed, but there are many masters and PhD students, they started working in this area. They have some preliminary results. I would like to thank IIT Bombay and DST and other funding agencies for the support, and also the International Society for Energy, Environment and Sustainability to give this opportunity to organize and also give the presentation. So thank you. And with this, I would like to invite Professor Nawaz for the last talk of this session. And we will take the question answer after that. So Professor Nawaz, please share your slide. Meanwhile, I will give you a brief introduction. So Professor Nawaz has done his MTech, BTech and MTech dual degree from IIT Kharagpur. And during his master's, he was work on polymeric membranes, where he tried to make certain patterns. In PhD, he has done his PhD from University of Massachusetts, and his area was silver recovery from the laundry waste water. So he joined IIT Bombay in 2019. And he won Young Faculty Award here at IIT Bombay, and there are many other awards such as Distinguished Doctoral Fellowships and Best Poster Awards. At present, he's working in electrochemical disinfections, ion exchange and absorption systems, resource recovery, bioremediations, PFAS removal and degradation, and also try to synthesize new nanoparticles for degradation of these pollutants. and also working on a produced water treatment. So with this, I would like to invite Professor Tabish, and now floor is yours. Thank you.
Thank you, Professor Swatantra, for this introduction and inviting me for this talk. Good evening, everyone. Today I will be discussing resource recovery opportunities from reverse osmosis concentrate. Though my talk is not centrally related to membrane science, but it has some peripheral importance and which affects the other areas of water and wastewater management. So, is my slide moving? Professor Swatantra?
No, Professor Nawaz. So I think there is some problem. Maybe you can try to share your.
Yeah,
now it's shared.
Yeah.
Now it's changed.
So resource recovery philosophy basically ties up with this fundamental problem of water crisis. And as we know that water crisis is basically caused by lack of freshwater reserves and also due to the pollution of caused by various human activities. So where resource recovery can fit in? So we see that we understand that water reuse is a possible way out of this water crisis, right? And water reuse can also help us in a lot of other ways, like it can help reduce pressure on lots of water sources. Also, there are locally controlled water use aspects and water equity issues. So water reuse can be a possible solution to a water crisis. And here, where resource recovery is relevant, like water treatment requires cost inputs and technological developments. And that is why 80% of wastewater is directly released into the environment without adequate treatment globally. Now, potential solution to this impasse is basically resource recovery, where wastewater is considered not as a waste, but as a repository of resources. So also it has caught up with the concept of circular economy, where each stream in the system, in the process, is recycled and the useful materials are extracted and reused in the process. So also one of the potential and critical solution in augmenting water supply is desalination, particularly in the areas where fresh water supply is scarce. And if you go by the data, we are seeing the desalination globally is increasing, and it is reflected by the number of plants that has increased and also the global desalination capacity that has increased over time. And roughly 50% of these desalination plants use reverse osmosis process. So this reverse osmosis process typically produce roughly 65.5 million meter cube water per day. And it amounts to roughly recovering 45 to 55% of the influent seawater. So out of that, so we can say that up to 45 to 55% is also generated as waste. So this waste we are mainly interested in because it has lots of minerals that can be economically recovered, and also water can be recovered, and water reuse can be implemented in the process. So why this, if we look at the schematic, the RO concentrate, which is denoted by the red stream, is limited by the rising optimum osmotic pressure. So if the osmotic pressure rises, which rises due to the increasing concentration on the permeates concentrate side, so we can see that permeate flux basically decreases, and water recovery also decreases with rising osmotic pressure. So which means that we cannot go beyond a certain osmotic pressure, and because that will require to impose higher transmembrane pressure, and membrane has certain capacity to withstand that kind of pressure. So we expect that even if we design our RO process to the best of thermodynamical energy capabilities, we can expect that certain retentate will be generated. And right now, like based on the available data, roughly 141 mega million cube per day RO concentrate is generated. Roughly 31% comes from RO processes. So this RO concentrate is rich in mineral, and since the water recovery rate is around 50%, we can expect that the concentration in the RO concentrate will be roughly twice of the seawater. So the minerals that are predominantly present are these, but there are trace minerals like lithium, rubidium, cesium, germanium, uranium, which have very high market value, and they can be recovered to improve the economic aspects of resource recovery. Also, the present method of disposing of RO concentrate is not environmentally viable for long term, because it can lead to deterioration of soil quality. Also, when it is discharged in, like, put back in the sea, it can lead to like lots of issues like pH imbalance, temperature, and also dissolved oxygen reduction. And also it is discharged through some copper and lead pipe. Those metals also leach, and then eventually they find their ways in the seawater, which is not very beneficial or for the sea organisms. Also, it contributes to cost, like roughly 5 to 33% of the overall cost of desalination is spent on concentrate disposal. So if we can think of some resource recovery methods, then we can not only get some economically valuable material, but also we can enhance the water recovery, and we can approach the zero liquid discharge ideal that is aimed for. So different advantages we have from resource recovery from RO concentrate. Of course, water recovery, mineral for economic benefits, also reduced overall environmental impact. So typical, like some of the resource recovery candidate that we have gleaned from RO concentrate are these, and the calculation has been done on the basis of 50,000 meter cube per day of RO concentrate generated, and it is based on like what is the market value of that particular element, and also what is the concentration of element in the RO concentrate, and how much is the operating cost that comes. So that calculation has been done, and based on that, like the elements that are economically extractable are rubidium, lithium, iodine, bromine, magnesium, potassium, sodium. So these are the candidates that can be feasibly extracted based on their market value and the concentration in the RO concentrate. On the left hand side, we have some of the elements, but these are like economically challenging to extract. So there are different technologies for treating RO concentrate, and my research has just started in this area, and I am working on lithium and rubidium recovery right now using ion exchange method. But in any any resource recovery method, the first thing is that we should identify the extractable resources which have some economic values, and then we need to showcase the technology and then assess them critically, and then finally decide on the technologies that is going to be used. So based on our assessment, we have chosen to go for precipitation and ion exchange based methodologies, which we are currently developing in our lab. So to give you a brief idea about some of these technologies, so I'll go each one of them separately. So first one, like solar evaporation, is perhaps one of the oldest technologies that are being used, particularly in seashore areas, where pans are created. The first pan is basically the influent pan, incoming pan, and then there is evaporator pan and then crystallizer pan. And in these pans, like based on the saturation index, the minerals are crystallized and recovered. So it is basically a pre-treatment process to concentrate brine, and it is simple to design and operate. But the key issue are that it requires large land area, and also longer duration is needed, and it can cause soil and groundwater pollution. So it can be though useful for minerals with high concentration like sodium chloride, potassium chloride, gypsum, and magnesium sulfate. But there is no water recovery opportunity there. There are few membrane-based methods which are very useful in this regard. One of them is electrodialysis. In electrodialysis, we have a series of anion and cation specific membranes, which are placed perpendicular to the electric field and in an alternate fashion as shown in the schematic. And it can separate like monovalent and divalent cation also by using monovalent selective anionic and cationic membrane. So results have shown that high purity sodium chloride can be obtained, and also in some of the papers like lithium, magnesium hydroxide, and bromine gas have also been reported. But the key issue is in electrodialysis is the scaling. Another membrane-based method is membrane distillation crystallization. So it can be useful for minerals with high concentration and which have high supersaturation, such as sodium chloride and magnesium sulfate. So here we have hydrophobic porous fiber membrane, which gives large surface area, and that way it reduces the temperature of evaporation. And there is a circulating crystallizer unit and a crystal recovery unit where after the water that is evaporated and passed through the membrane unit, hydrophobic membrane unit, the retentate is further treated in a crystallizer and crystallized and recovered. So it has like potential of more control on the crystal size and the crystal growth. Another membrane-based method is forward osmosis, where high concentrated, like high TDS water, like RO concentrate, can be used as a draw solution. And it is useful for concentrating solution, and it can have a high water recovery. But resource recovery opportunities are basically limited. Then one of the most like used method in pre-treatment step is chemical precipitation. It is effective for divalent and high concentrated supersaturated minerals, ions, particularly calcium and magnesium, because it is governed by ionic strength and pH of the solution, and some of these divalent cations precipitate at high pH values. And it can also reduce scale forming tendencies in secondary RO and can be used for like pre-treatment process for secondary RO process, and also it can be used as a pre-treatment step if we are going to eliminate the impact of divalent cations in our further treatment process. There is this ion exchange or adsorption based method is basically useful for trace elements, because we can functionalize our resin or adsorbent with a certain targeted recovery of certain elements, and we can implant certain functional groups over them. So it can be very useful for targeted recovery, but it requires integration with other processes such as pre-treatment step for removing high valency ions like calcium and magnesium, and also it requires post-treatment step like desorption and then recovery from the spent regenerant. So, but it can be used multiple times if we can regenerate the resin, and if we can recycle the regenerant. So the future direction in this regard is that, of course, RO desalination is crucial for increasing potable water availability, and its application is expected to increase in future. Therefore, it will lead to more and more generation of RO concentrate. So utilization of RO concentrate for resource recovery and water reuse is imperative, and identification of resources to be recovered from RO concentrate is also required. So, and once the resources are identified, the treatment technology specific to that resource needs to be developed. And that has to be this, once this technology is developed, it needs to be integrated with the currently operating RO desalination system for like how it overall fits in the scheme, that whether it enhances the water recovery, at the same time it recovers certain resources and also achieve zero liquid discharge and water reuse goals. For recovering high concentration species from RO concentrate, chemical precipitation, crystallization, and membrane-based methods can be useful. And for trace mineral recovery like electrodialysis, adsorption, ion exchange, liquid-liquid extraction can also be explored. The species that can be profitably recovered include like sodium, potassium, calcium, magnesium, rubidium, indium, cesium, lithium, strontium, bromine, boron, and uranium. So with this, I come to the end of my presentation. So I would like to thank my MTech students, Kalpesh and Vishal, which helped me in preparing this presentation at the very last moment when I received the call from Professor Swatantra for this. So I'm thankful to them. And I'm also thankful to Professor Swatantra to giving me this opportunity. And thank you, audience who came to listen to me. Thank you.
So thank you, Professor Nawaz. So with this, we will going to take the question answer. But before that, I would like to summarize the all 4 talks. So the first talk was given by Professor Kasher, where he's talked about silica scaling on mimetic surfaces. He has shown different results based on the QCM analysis, QCM dissipation and precipitation analysis, where he has his group was modified different surfaces with different functional group, and then they showed like how the silica precipitation can affect it with different kind of functional groups. And then further those studies get supported by the AFM studies, where they will successfully explain the interaction energy and how these different functional group can deposit and which can repel. And on the basis of that, we can develop a successful strategy to make a new generation of anti-scaling membranes. After that, Professor Arnush has talked about on laser-induced graphene surfaces, membranes for using for water treatment, where he had talked about different doped laser-induced graphene, including silver and sulfur. And he has shown quite interesting results for degradation of different pollutants, including emerging contaminants, which are creating a lot of news nowadays, along and also for a chromium. So and the overall talk of Professor Arnush shows that at the end he summarizes like laser-induced graphene has huge potential, and that's why I would like to add, like every week nowadays 2 or 3 articles are coming on the based on laser-induced graphene, and a lot of papers started coming on sensing thing, because it's very easy single step process to make these laser-induced graphene surfaces. And then I talked about a different kind of textures what we can use to control the biofouling. So along with other fouling, biofouling is one of the reason which increasing the overall cost based on membrane treatment. And I have talked about the texture, how they can play a very crucial role, and laser-induced graphene and polymer brushes has a potential. There are many others, but I have talked about mainly these 2. At the last, Professor Nawaz has talked about the resource recovery opportunities, and he has talked about what are the major challenges if we are disposing the brines. There are different kind of chemicals in that, and also these high salt concentration can cause a lot of ecological problems. And also the disposing these RO concentrate or brine, it's also involves some kind of cost. So if we can go for a resource recovery by using these RO concentrate, it's going to give us the economic value, and that's going to compensate the what we are going to invest to dispose these RO concentrate or brine. He has talked about a different technology for resource recovery, such as electrodialysis, membrane distillation, crystallization, and at last he has given the what can be done and what kind of minerals or what kind of things we can successfully we can recover, which are it's going to help the overall going to help to increase the decrease the cost and reduce the overall ecological impact of brine disposal. So with this, I will start with the question answer. So there are a couple of questions which already answered. So I think attendees can see those responses, and we'll see, like, if time will permit, we can also discuss if some of them it's not answered yet. So first, I would like to start with the first question, which is for Professor Kasher. So it's while doing surface modification during self-assembly, what is purpose of using silica? What other inorganic materials could be employed except this? So I think, like, there is
Okay.
yeah.
Okay, so let me say the silica particle was used to mimic the silica particles or nanoparticles in solution on their intermediate stage between the solute and the mineralized or solid state of the silica. So the silica particle was used to mimic actually the solution, while the surfaces are mimicking the membrane or any surface of study. So I don't know if I understood the question properly, but I hope that I answered. But if please, I would like to have some feedback if I understood the question properly.
Okay, so I request the attendee to just answer. Like, I think that was the meaning. Like, yes, you are mimicking the silica, and we have to mimic the what kind of colloidal, like what kind of scaling we are targeting, and for that the modification was done. So thank you, Professor Kasher. So I
Yes.
think the
Yes. I would like I would like to add that in fact it is an important question by itself, because our hypothesis was that a silica colloid that we used for the AFM studies, our hypothesis was that silica colloid will be able to mimic or simulate the behavior of the silica scaling, the silica particles that are formed in the solution. And according to the results, because we observed the same trend or the same influence of the different surfaces, we can understand now that this choice was relevant. It was indeed mimicking the silica scaling. And this is so the question is very important, because it is an assumption that we did in this research, which is completely not trivial. Thank you.
Thank you, Professor Kasher. So the next question is for Professor Arnush. So here it's written: can we use LIG for oil producing industries? I wish to be enlightened about its recyclability and how to do so.
Yeah, thanks for the question, Riza. I think, oh, can you guys hear me? Because it
Yeah, we
seems like
can hear.
everything's frozen.
We can hear you.
Okay. Okay. So yeah, you know, what I haven't done any studies yet with LIG and oil. However, I hope to show that that it's versatile, so that it may be possible to use it for food oils or separation of oils in that industry. Since you can change the hydrophobicity, super hydrophobic or super hydrophilic, or perhaps put in some properties in that surface to get oil rejecting properties. So I think it's got a lot of potential, and we just have to, I haven't seen anything yet for that, but maybe in the future.
Thank you, Professor Chris. I think the next question is also for you. What was the molecular weight cutoff of the membranes used for micropollutant degradation?
Yeah, the membranes we used were like microfiltration or even bigger. So there was no molecular weight. So all of the micropollutants could easily pass. There was no rejection of the micropollutants in the membrane. So it was really degradation using, well, either adsorption onto the membrane or or degradation electrochemically.
Thank you, Professor Arnush. So I will move to another question, which is for Professor Nawaz. So it's I think Professor Nawaz and me both can answer. So it's I have how to approach design of RO system for home use. Economical solution. Is it an economical solution?
Professor Swatantra, you are going, or should I go for that?
So you can go first, and then I will add if required.
Okay. So the question is how to approach design of RO system for home
use, and economical solution and question mark. So it means he's trying to understand whether it's an economical solution to design a RO system for home use.
Okay. So like RO system at home, in my guess, like it should be dependent on the influent water, right? So the influent water in RO system will not have, in domestic water will not have too much high TDS. So I think like we don't require too much high of like in terms of material, it should be fine. Like a typical RO system shall work. And from energy perspective, like we don't need like too high on energy side also. So I don't know how to address it from economics perspective. Like, is he looking for resource recovery or something from like one of the key issue in RO at home also, the water recovery is very poor, like roughly 30% or something, right? So lots of water goes to drain, which is not a very good practice for in a long term. Also, it increases some of the pollutants concentration, particularly nitrate. I have read somewhere that it provides like some 3 to 5 milligrams per liter of nitrate or something. So that should be looked into. I think from environmental perspective, it is more a valid question rather than from economic perspective in a household for RO water system. What do you think, Professor Swatantra?
So I agree with you, Professor Nawaz. So anyhow, it's a very relevant question, and I will move to also to Professor Kasher and Professor Arnush. But before that, I just want to build certain background for that, because I think it's asked by Sachin. And in India, what happening? Even we are having a very good supply of water, but sometimes the quality is not adequate and it's not uniform treatment. There are many small units of RO people are using at home. So like there are certain places where the supply water is quite good condition. I can give you example like such as in Bombay. the kind Mumbai, the kind of water we are getting, it's a very good quality, and I have put it one of the best quality RO from one of the company, and I just try to understand how much recovery and other thing is there, and ultimately what we are getting. So what we have seen, it's the treated water is almost have very low TDS, which is not going to be really good for consumption. And also it's just like Professor Nawaz said, like the it's around 30% water what we are getting. So for making 8 liter of water, it's throwing 16 liter of a good quality of water. So that's one issue. Yes, what kind of input water we are getting. And if you are talking about some remote places in India and some of the places in the Rajasthan where we have really high TDS water and it's not treated, then obviously we can go for this kind of RO systems. In terms of economics, like obviously if you have it's all the things depend what kind of quality of input water you have, and most of the traditional technology, if they are failing, and then obviously you have to move to the membrane technology, and if we have really high concentration of salts and other things, so we have to go for RO. How we can design, there are multiple things we can do to reduce the cost apart from these fouling and other things. We can reduce the overall carbon footprint by integrating these systems with renewable energy sources. Like if you are in a remote area, a remote village or something, so solar PV panels can be integrated, and that can help to reduce the overall carbon footprint. And other kind of the things depend on what kind of input water and what kind of pollutant you have. We can design a modular systems where, for example, some places the overall water is quite good and you have only the contamination of arsenic. So you can have a pre-treatment system where we can reduce the arsenic for that level, for a consumption level, and then just ultrafiltration is going to be enough. So it's depend, generally like in the most of the condition, if the water quality is good, RO is not a good option. There is the alternative of like nanofiltration and ultrafiltration can be adopted. With this, I would like to invite Professor Kasher to talk about this, like is it feasible or it's a good idea to make these RO system at home or not. So I think I have given some background, which Sachin, I think, is asking in what term.
Okay, so thank you, Professor Singh. So the RO systems, I think that for systems at home, it will be a bit expensive and difficult to operate because right now the technology is, of course, it is optimized for quite many years, but today the large-scale facilities succeeded to reduce the price of desalinated water to a reasonable price that it is now operated in a large scale in Israel and other places. I'm afraid that, of course, it depends on the investment of, and but I think that doing it for home use, it will lose the advantage of large scale optimization that was performed, and it will be still too expensive, I'm afraid. So the industry can use it for, of course, for locally, and it is used in. It can be used to obtain a higher purity of water for certain, for certain reasons. So in industrial scale is possible, but I'm afraid that, to my opinion, today it will still be expensive for home use.
Thank you, Professor Kasher. So, Professor Arnush, if you want to add something in this.
Yeah, I agree with you, Professor Singh, that the recovery, and also with Dr. Nawaz, the recovery issue, in my opinion, is very big, because if you're only getting a maximum 30%, you're wasting a lot of water. A lot of water is going down the drains. So if you could recover that good water, then that might be possible. But if you're in a water scarce area, then you probably don't want to be doing that type of thing. And I also agree with you, Professor Singh, that it all depends on your water quality. You know, you don't need RO if maybe you're only wanting to remove some viruses or bacteria, and then maybe UF is enough. Or so I think it really depends on the water quality and what water quality you desire.
Thank you, Professor Arnush. So the next question is also to you. How did the nanoparticle were incorporated or doped in the membranes?
So these nanoparticles, you can dope metal nanoparticles in an LIG in two ways. One is to have the metal salt in the substrate, and then during the laser process, the lasing can also reduce that metal salt into the metal, and the nanoparticles are just embedded in the graphene. And the second way is, once you've got the laser-induced graphene, you can coat that graphene with your metal, a metal salt, for example. And then, like I showed, you can relaze the surface, and then you can also get your metal doped into the laser-induced graphene. So it's due just to the laser conditions. They create a reducing condition, and you get metal nanoparticles from a salt.
Thank you, Professor Arnush. So next question is Professor Kasher. It's like, what are the strategies to control the scaling, and how much the cost is associated with, because we talk about a lot about biofouling, but what is the potential of scaling and how much we are investing, because we know a lot of anti-scalant we use. So can you but just first give the idea about the strategy and then cost related to that?
Okay, so in seawater desalination, a lot of the scaling is by carbonate salts, carbonate precipitates, and this is controlled very easily by acid wash. So using organic acids mixed with water, this can be done. This is done periodically, and these types of scaling are quite reasonable to control. The problems are usually with the diverse and the other types of scaling. So as I mentioned, the silica scaling has its problems. In wastewater desalination, we have the phosphate scaling, and so other types of scaling will need specialized anti-scalants, which today are not efficient enough for silica and for calcium phosphate. There are anti-scalants that are efficient for calcium carbonate minerals, and these are used, of course, in the desalination processes. So except from the fact that the acid wash is very efficient, then there are also efficient anti-scalants for carbonate minerals. So I can say that for this reason, I mentioned in the research that I described before, the other strategies will be needed in the future to cope with some specific types of scaling that do not have the efficient antiscalants. So these types of minerals, of course, depends on the source water. And in brackish water, we have, because we have large variations of the water chemistries, which depends on the water source, the geography, and the types of aquifers. I think that the other strategies will be needed. For example, membrane modifications that will be specific to a certain source type of water.
So thank you, Professor Kasher. So the other thing, it's the cost associated with this, like how much money, like we are investing because of these scaling, and when we are using this anti-scalant and other things. So there is some any rough estimate, like what is the cost associated with this in a percent, like when we are running a plant, a big RO plant?
Yes, so so that will depend very much on the type of RO technology. As I mentioned, in the seawater desalination, it is part of the, I think it is a smaller part, but of course the energy in seawater desalination, the energy constituent will be more than a third of the expenses, so it will be the highest. Whereas when we are dealing with other types of water, feed water, like brackish water, the salinity is much lower. That's why the energy demand is much lower. So then the fraction that we spend on scaling and operation, solving the operational problems will rise. Of course, as I mentioned, because we have very different types of source water, and also so it will be difficult to say exactly the price for treating the scaling, but I can surely say that in brackish water desalination, the dealing with scaling will be much larger than in seawater desalination, and it will sometimes it will be it will determine whether this technology is at all economical or not.
Thank you, Professor Kasher. So we will move to next question, which is for Professor Nawaz. So can you give an idea about where we can come up with the integrated systems? So where we can do a RO plant coupled with some system where we can go up to a zero liquid discharge concept?
Yes, Professor Swatantra. Like the main issue with like in RO system is like rising TDS on the concentrate side. So and typical, if we go for seawater system, like a typical recovery is around 50% water. So if we are going for a zero liquid discharge, if the concentrate that is say roughly coming at around at 70 gram per liter of TDS, if we can reduce the TDS to say initial level, say to 35 gram per liter, then we can go for a zero liquid discharge. Suppose we get 100 liter of water, we create 50 liter of waste and 50 liter of recovered water. And then if we reduce this 50 liter of water again to 35 gram per liter level, then we can recycle it and it will be continued in the circle. So we will, next time we will get only 50 liter and we will put the recycled 50 liter and we will get like 50 coming in, 50 going out, and 50 will be continuously in the loop. So idea is to reduce the TDS to at least to 50% of the original TDS of the RO concentrate. If we are able to do that, I think we should be very close to zero liquid discharge.
Thank you, Professor Nawaz. So I think another question is that like I think you can able to answer that. Like, what happen if we inject these RO concentrate in deep down water table?
So, like, of course, alkalinity will increase, right? Because we are putting in like carbonates are there, right? So it will increase the alkalinity. Also, calcium salts, magnesium salts are increasing. It will increase the hardness, right? So the water will have more hardness, more alkalinity, and that can be an issue, right? And it will dissolve like acidic, like we will have acidity also if more carbonate is coming in, right? So those things, it can have some pH imbalance, hardness issues will be there if we put it directly in the groundwater system.
So, I want to know the opinion of Professor Kasher and Professor Arnush. Like, what kind of strategies, because Israel has 5 big plants. So what kind of strategies Israel is now using to dispose of these brine? And if they are directly dumping into the sea, then what is the future plan to tackle with this brine?
Yes, so I can say that that in Israel the seawater desalination is the brine is disposed directly to the sea in all of the plants, and the problem is, of course, as I mentioned, the problem is in brackish water desalination, because inland desalination plants need to dispose the brine. This can of course have severe effects on the freshwater aquifers if they are, or the environment. But in the seawater desalination plants today, all of them around the world, they dispose the brine to the sea. There are, for several years already, the Oceanographic Institute in Israel, and I'm sure also other places in the world, conducted intense monitoring of the ecosystem of the marine environment around the desalination plants, to try to understand the effect on the ecosystem. I can tell you that that these monitoring or these studies until now they showed that the effect is very local, about hundreds of meters in radius around the disposing site, because you have of course increased salinity, which can affect the microorganisms, the plankton in the sea, but it does not have, at least for until now, they did not see any large or wider effect of disposing the brine. We have to remember that the brine of reverse osmosis plants, as was mentioned before, it is maximum twice more concentrated than the seawater. So this is the practice today in seawater.
So thank you, Professor Kasher. So Professor Arnush, if you can add also something on disposal of the brine from the desalination.
No, I don't think I can add. I think Professor Kasher summarized everything fully.
So thank you. So the next question is, I think, to Professor Arnush. How do we dispose the used membrane? Do we send it to landfill, burn, or recycle? If the disposal is landfill, which category of waste will be? If burned, then it will cause air pollution problem. If recycled, how many times can we reuse and how? And there is an additional question, I think, can we use membrane for pesticide removal for pesticide industries, like that? So I think one by one, it's better to
Yeah, so I'm not exactly sure about this. I know that a lot of membranes are just sent to the landfill. I'm not sure if they're burnt. I know that there are different ways to recycle membranes. just as you would recycle other polymers or plastics. But I have seen articles where people suggest how to recycle membranes. So I'm not an expert in disposal or recycling, so I can't tell you if it's landfills or burnt but I can just general knowledge that, of course, if you burn the polymers, you might cause air quality problems, but you have to then consider, you know, what is the volume, and so I think you know, in the biggest desalination plants, you know, you're looking at 40,000 modules in one of those plants. You know, a big 1 meter long membrane module, and they replace about 3,000 to 5,000 of those modules per year. So yeah, it's all a matter of understanding how much is disposed and what would be the best way to do it.
So thank you, Professor Arnush. So Professor Kasher, can you add like what is the general practices in Israel right now they are using to dispose these modules? If you have any like information on that.
Yes, I don't have much to add on top of what Professor Arnush said. I can only say that he did when the plant is operated properly and also with a little bit of luck, the membrane modules could last for 8 to 10 years. And this is, I agree with Professor Arnush that this is a matter of concern for any other industry that has a plastic disposal. So this is a plastic disposal that has to be taken care, and I'm not familiar of any specific practice of disposing these membranes.
Thank you, Professor Kasher. So the next question, I think, if Professor Arnush can add, like regarding the membrane used for pesticide removal.
Which question is that? I don't see it.
So it's in the same, like from Riza, it's written like, can we use membrane for pesticide removal?
Yeah, that I would say we can use membranes for pesticides. You know, pesticides usually are organic molecules, so that would fall under perhaps emerging contaminants or micropollutants. And you know, we need to understand what are the properties of those pesticides, and if the membrane can stop them. So of course, if the membrane has a pore size smaller than the pesticide, then you'd be able to separate. However, some pesticides, they're an organic molecule which can be absorbed into the membrane and then diffuse across. So even if you've got an RO membrane, there are different types of these emerging contaminants that can still pass even an RO membrane. So, you know, there are, you need to think of different ways to remove those types of compounds from the water. And you know, I hope that from my presentation, like this electrochemical way of removing those type of things may be a solution, but there could be other solutions as well. For example, adsorption or those types of things.
So thank you, Professor Arnush. So I just want to add also, like just what Professor Arnush talked about, these electrically conductive membranes. So there is a class of new membranes where on the same time with separation, we can do degradation. So possibly that can be a solution for these things, where most of these emerging contaminants, because of their smaller size and absorption properties, the rejection even through the RO is not that great. So now I think we have 6-7 minutes. So there are certain very questions like which I would like to get opinion from all the panelists. So one of my question is like, what is the future like of these hybrid systems? Because like when we are talking about these membrane technology, so because as these membranes have a very good, we have from starting from ultrafiltration to up to RO, and also now these concentration based thing like the FO we have, and also we have membrane distillation. So the question is like, what is the future of a whole system, a whole water wastewater system or desalination system, where by using these kind of hybrid systems, we can get maximum efficiencies and also the cost effectiveness. So I think Professor, I would like to invite Professor Kasher for his opinion for this.
So the future is, I think, several directions. The hybrid systems, of course, they are possible to do and already were done in the past. I think that the reverse osmosis membranes are very efficient in terms of salt separation or salt rejection. So other applications will need more specialized membranes and or hybrid systems, as you mentioned, because today, for example, the treatment of wastewater is a growing field, and until some time ago, the wastewater treatment was performed to be able to dispose it to the environment. But today, we can see that in many places the wastewater is seen as a resource, because the wastewater can be treated, and indeed they are used for industrial and agricultural applications. But if we want to have treated wastewater with higher purity, and this will need efficient and specialized technologies that are not that will not be exactly the same as the seawater or brackish water desalination, because we have different the water is very different, the salinity is low, there is organic load, high organic load, and possibly some toxic pollutants. So the treatment of this type of water will be, I think, the more advanced in the future.
Thank you, Professor Kasher. So Professor Arnush, what is your opinion about these hybrid systems?
Yeah, I think you know, the water technology, in my opinion, is very highly developed, and there's a lot of excellent technology out there, and so I think that designing off-the-shelf hybrid systems can really address many of the challenges seen today in the water sources. So yeah, you know, of course, we're in academia, so we're trying to innovate and find, I guess, new technologies to address perhaps questions which are still not completely optimized with the existing technology. But yeah, I think that combining existing technology can already address a lot of the problems out there.
Thank you, Professor Arnush. Professor Nawaz, what is your opinion for in this regard?
I think like integrating some of these technologies can help, like of course in like resource recovery, like if we can use FO and RO, like we can create like a use of this wastewater as a draw solution, and also like if we are to reach like the zero liquid discharge standards, like some of these technologies can be useful. Resource recovery, as I said. Also, like fouling issues, maybe like from process perspective, something can be done about that if we integrate like different kind of membrane systems. So I'm not very much actively involved in membrane operations, but I'm telling you from the resource recovery perspective that it is possible to achieve that standard of zero liquid discharge and reduction in fouling and all.
Thank you, Professor Nawaz. So yes, I have same opinion what Professor Kasher, Professor Arnush, and you have added. And these hybrid technologies, they are bringing a lot of things. So there are certain places where we are not looking for the money, like the cost effectiveness, but we are looking for a maximum efficiency, such as a space application. Like we are trying to, the scientists are trying to develop a certain new technology where they can get 99-100% of recovery using this kind of hybrid system. So we can go for long exploration, such as like going Mars or even far than that, which is quite difficult at present. With present technology, we have to carry a lot of payloads of water if there is 4 or 5 member of crew is going for that. So these hybrid technologies have a lot of future, and with that we will able to address there are many problem like what you have said, like FO can address. There are many fouling kind of things which FO and RO integration or FO with MD integration can give us a very good results. So we are going to close this session in few minutes. So just I have one question from all of you. What is the the talk was on desalination and wastewater treatment by membrane technology. What is the other? Is there any technology which can compete with the membranes, or the membrane are going to rule for next 20 to 30 years? So, Professor Kasher, I want to know your opinion regarding this.
So, I think that the membranes are going to rule in the next 20 or 30 years. But there are several unique cases where other technologies will be better. I mean, if I understand correctly, you are asking about saline water, so either
yes,
seawater or brackish water. So to desalinate saline water, I think that right now and in the next 20 years, the membrane will continue to take over. I mean, it is a process. But as I mentioned, there are unique cases. For example, when you have some heat, excess of heat, for example, from a power plant, and that can be used for maybe for a membrane distillation or other processes without membranes that will use the heat. Or maybe some in quite unique circumstances, other technologies, of course, will be more attractive. But in the normal or regular situation, I think that membrane technologies will be still much more efficient.
Thank you, Professor Kasher. Professor Arnush.
Yeah, so I think membranes will rule. There's huge research continuing on membranes, so I think membranes will only get better in the future. All around the world, people are trying to improve membranes. So even though membranes right now are highly efficient and highly, they're like a commodity. So they're highly efficient and they're highly effective. They're cheap right now, producing cheap water, especially for desalination. So I think even with all our the the research going on, including research in companies, I think that the membranes are just going to get better in the future.
Thank you, Professor Arnush. Professor Nawaz?
So I agree with Professor Arnush and Professor Kasher. Membrane, of course, is has a future, but I think standalone, it may not be able to solve much of the problem. I think it will create some of the problems too. So there can be some integration with other systems like electrochemical or maybe biological systems also. So I see that the future is integration with different kind of arrangements.
Thank you, Professor Nawaz and Professor Kasher and Professor Arnush. So I agree with all of you, and that's why there was the one question we, because of the time, we were not able to take it. Like, what is the main role of microbiology in membrane technology? So there is these MBR system, so which are replacing the activated sludge process in wastewater treatment, where we are trying to integrate the microbial degradation along with the membrane, and we are able to get the fruitful result. And I completely agree with Professor Arnush. So the research is going a lot in this area, and now the people are trying to come up with these biologically inspired membrane like aquaporin and other things. So in future, probably we are going to have very good quality of selective and high permeable membranes. And the overall, the problems of cost and other things what we are facing, it's going to be reduced day by day. And at least for desalination and wastewater treatment, for surface water treatment, probably we don't need these membranes, but for desalination and wastewater, we need these membranes. And with the new development, with the new generation of membrane, coupling with these electrocatalytic properties or with these new aquaporin or biological inspired membranes, they are going to rule for next 20 to 30 years, unless until there is some very drastic change in technology or something is going to happen. So with this, I'm very thankful to Professor Kasher, Professor Arnush, and Professor Tabish to accept the invitation and give their talk on this and talk about on these important things related to the membrane technology. And I hope we will able to come up with some certain things which new and try to solve the major problem, including the what the question talked about, the membrane recycling. So I think Professor Chris, if we can, he's already in that process where they can use, and I also was part of that, where we can use this waste membrane to convert laser-induced graphene filters, and that can be again used for some fruitful purposes, using for degradation of contaminants or disinfection and all those things. So with this, I'm really thankful to this International Society of Energy, Environment and Sustainability to giving opportunity to us and to talk on this desalination and wastewater treatment using membrane technology. So thank you, Professor Arnush, Professor Kasher, and Professor Nawaz. And with this, I request ISES volunteers to take over this session. And if there is any further instruction they can give, otherwise we will close the session. So thank you, everyone. Thank you, Professor Arnush, Professor Kasher, and Professor Nawaz.
Thank you
very much.
We are closing
You're
the
welcome.
session.
Thank you very much. Thank you.
Thank you.
Goodbye.
Goodbye.
Goodbye. Thank you.